Here we are at the penultimate concept map for our course, and here is my concept map that I've crafted as a way to represent and summarize the key concepts and the relationships to one another from this week's chapter. As you will note, this chapter also involves the logic of hypothesis testing, and we are working with a situation where there are at least 3 different sample means. Before we begin, I would like to offer this editorial remark. So far in this course, we have not relied upon various pieces of statistical software like SAS, SPSS, Minitab, etc., etc. And my argument has been that because, for the most part, we're not dealing with large data sets, there is no need to use these pieces of software. Some of you may have found some use in using a spreadsheet, and that is fine. And as for an analysis of variance, a spreadsheet application like Excel does have the tools within it to help you do an analysis of variance without getting caught up in all the formulas. All the same, I am attempting to slow down the process so that you may have an opportunity to try to understand the concepts, how they're related, and what may be going on behind the scenes. It's not possible to have this kind of understanding if one simply plugs in a whole bunch of data into a piece of software and get an answer out without really having a good enough understanding of what's going on. Okay, enough editorializing. Analysis of variance. An analysis of variance can be viewed as multiple tests that look at differences of means. But this, in practice, statisticians tell us, is not a wise thing to do. In other words, doing multiple applications of the test where we're comparing one mean with another, then comparing one mean with another mean, and so on and so forth, creates type 1 error that grows and grows and grows. This is a big problem. But moreover, in terms of practice, this would mean doing the same kind of test multiple times over and over and over again. So for example, if we had 3 samples, we would need to do 3 t-tests. If we had 4 samples, we would need to do 6 t-tests. If we had 5 samples, we would need to do, well, you can see it's just getting more and more unwieldy. So the analysis of variance helps us in that regard. For this course, we are only going to pay attention to one kind of analysis of variance, or an ANOVA. And so we are going to look at what is referred to as a one-way ANOVA, which analyzes the relationship between one variable and another variable. Two-way ANOVAs analyze the relationship between a variable and 2 other variables, and we're not going to pay attention to that here. But just keep note that there are many different kinds of ANOVAs that one might do. As with the previous 2 concept maps, we are going to follow the logic of hypothesis testing, and so there are 6 steps to follow. 1. Formulating a null hypothesis. 2. Setting a level of significance. 3. Identifying a critical value. 4. Calculating a test statistic. 5. Evaluating the test statistic in light of the critical region or region of rejection. And 6. Making a decision about the null hypothesis. As you can see, there's a lot of ground to cover, but if we break it down bit by bit, it's certainly quite doable. So let's start off with step 1, formulating a null hypothesis. It's stated in the usual form, H0 is equal to the first mean, which is equal to the second mean, which is equal to the third mean, which is equal to however many means or populations you have. In any event, the null hypothesis, as our testable hypothesis statement says, that there is no difference between all of the means that we are testing. The level of significance, step 2, is set in advance by you, the researcher. Not much more needs to be said about this. You'll either set a level of confidence at 95% or 99%. You then need to identify the critical value, and this requires knowing the degrees of freedom. Except in this case, we need to know 2 different degrees of freedom. 1, the degrees of freedom for within groups, and 2, the degrees of freedom for between groups. The degrees of freedom within groups is denoted by df sub w. This is just notation. We also have a similar notation for degrees of freedom between groups, denoted as df sub b. The degrees of freedom within is easily calculated and is equal to n minus k, where n equals the number of elements within each sample, and k refers to the number of samples or groups that are being tested. For the degrees of freedom between, again, this is also fairly straightforward. It is k minus 1, where k is a number of groups or samples. And both of these results, the degrees of freedom within and the degrees of freedom between, are both used to calculate the critical f-value. This brings us to step 4, where we are calculating a test statistic. The test statistic has a name and is referred to as the f-statistic or f-ratio, and it is defined as the mean sum between divided by the mean sum within. To calculate this expression, this ratio, we need to go through a few different steps. But all in all, we are calculating a ratio of the estimates of the between group variation and comparing it with the within group variation. To do this, we need to do a number of different calculations. Starting off with the group means for each treatment or sample, we then need to calculate what is referred to as the grand mean. We also need to calculate mean squares and sums of squares. In the case of mean squares, we need to do this calculation for within groups and between groups. And in both instances, there's annotation to describe two different calculations. So we have mean squares within and mean squares between, or ms sub w and ms sub b. In the case of the mean squares within, this is equal to the sum of squares within divided by the degrees of freedom within. And the mean squares between, or ms sub b, is calculated as sums of squares between, or ss sub b, divided by degrees of freedom between, or df sub b. And although we've previously calculated the degrees of freedom within and the degrees of freedom between, we still need to calculate the sums of squares within and the sums of squares between. And so to complete this cluster of concepts, we return to sum of squares for within groups and between groups. The sum of squares within, denoted as ss sub w, the sum of squares between the groups, denoted as ss sub b, where the sums of squares within is equal to the sum of squared deviations across all groups, and the sum of squares between, which is denoted as a weighted sum of squared deviations for all treatments. More details of these calculations or formulas can be found in your textbook. This brings us to step 5 in the whole process of conducting a hypothesis test. Step 5 being evaluating the test statistic in light of the critical region or region of rejection. And we do so by comparing our calculated test statistic with the critical f-value. Our last step then, making a decision based on the null hypothesis. Once we have compared our test statistic with the critical test statistic, we may conclude that there is a difference or there isn't a difference between any or all of the means. Here's the thing. We cannot tell where any of the differences might exist, but we can if we use another test, and that test is called the Tukey's Honestly Significant Difference Test, or HSD. And this requires another test statistic called the Q statistic. And at this point, I'm going to pause. I won't continue on any further, but I will simply invite you to return to your textbook to review the materials that address the use of the Q statistic as a way of determining where those differences might be. And of course, last but not least, you must remember that maybe you have committed an error in your decision making. But for all intents and purposes, we'll end there. But I will say one more thing. This test requires that our variables have to be at the interval or ratio levels of measurement. In fact, the previous test and the test before that, where we're looking at hypothesis testing with one sample mean and a hypothesis testing with two sample means, our variables need to be at the interval ratio levels of measurement. And in this case, when we do an analysis of variance, we are comparing at least 3 different treatment groups. In the previous example, we were looking at 2 different treatment groups, if you will, or 2 samples. And in the chapter before that, the concept map looked at 1 sample in our test. And with that, I'm going to have a darkroom moment, but we'll see you next time with our final concept map that looks at correlation and regression analysis.